Have you ever come across a solution to a coding problem that's so clever, it almost feels like magic? Well, that's exactly what we're diving into today. The Boyer-Moore voting algorithm. It is just a beautifully efficient way to find a clear winner in a whole mess of data. And trust me, by the end of this, you'll see why it's a total masterclass in problem solving.
Okay, so picture this. You're running an election, and you've got millions of ballots. Your job is to find the candidate with the majority of votes. But here's the catch. You can only use two tiny variables to keep track of everything. Two. How could you possibly do that? It sounds kind of impossible, right? Well, that is the exact challenge that this algorithm solves, and it does it so elegantly. So in more technical terms, what we're really hunting for is the majority element. Now, this part is really important. It's not just the item that shows up the most. It has to appear more than half the time. So, in a list of 10 items, our majority element has to show up at least 6 times. This strict definition is the secret sauce that makes the whole algorithm work. Now, if someone threw this problem at you in an interview, a couple of ideas probably pop into your head right away, and they'd work. They're just not the greatest. Let's take a quick look at these obvious but not so great solutions. First off, you could use a HashMap. Just go through the list and keep a running count of every element. This is really fast. It's a single pass, which we call ON time. The problem? Memory. You need to store a count for potentially every unique element, so that's ON space. The other common approach is to just sort the array. If a majority element exists, once everything's sorted, it's got to be sitting right there in the middle. This is fantastic for memory. It's O1 space, but sorting itself is just a slower process, usually around ON log n time.
So there you have it, the classic trade-off, speed versus memory. But what if we didn't have to choose? What if we could have our cake and eat it too? Could we get that super fast single pass time and the amazing memory efficiency of using almost no extra space? Yes, we can. This is where the magic really begins. The absolute genius of the Boyer-Moore algorithm isn't some super complex math. It's all about a simple, really powerful shift in how you think about the problem. It reframes the whole thing. Instead of thinking, I need to count everything, it asks, how do I find the sole survivor? So the algorithm starts with this core idea. What if we treat every element like it's a vote for a candidate? And now, imagine that every single vote for a different candidate has a very special power. The power to find a vote for the current leading candidate. And just completely cancel it out. Poof! A vote for candidate A comes up against a vote for candidate B, and they both just disappear. So after all that chaos, what's left? Well, think about it. If one candidate truly has more than half the votes, that means they have more votes than all other candidates combined. So even if every single minority vote perfectly pairs up and cancels out a majority vote, there will still be majority votes left over. The winner is just the one who survives this process of elimination. I know this might sound a little bit abstract, so let's make it super concrete. We're going to walk through an example array and see exactly how this whole voting and cancellation thing works using just our two variables, a candidate and a count. All right, here's our array, 3, 2, 3, 2, 3. Just watch how these two variables change. We start with the first element, 3. So 3 becomes our candidate, and the count goes up to 1. Easy. Next, we see a 2. That's different. So it cancels out one of our votes, and the count drops to 0. Now, because our count is 0, the candidate spot is empty. So the very next element, a 3, takes over as the new candidate, and the count goes back to 1. But oh, here comes another 2. It's different, so another cancellation. The count goes back to 0 again. Finally, we see the last element, another 3. The count is 0, so 3 steps up and becomes our candidate with a count of 1. And that's the end of our array. And just like that, we're done. We've made it through the whole list, and our candidate variable is holding the number 3. And if you look at the array, that is, in fact, the majority element. It worked perfectly. So you might be thinking, okay, that worked for that one example, but how can we be so sure it's not just a coincidence? Why is this thing guaranteed to work every single time, as long as a majority element actually exists? It all comes back to that fundamental definition we started with. The majority element isn't just common, it makes up more than 50% of the entire set. Yeah, think of it like this. If you made a stack of all the votes for the majority winner, and then you took all the votes for every other candidate and put them together in a second stack, the majority stack is, by definition, always going to be taller. So here's the crucial takeaway. There simply are not enough minority votes in the entire array to cancel out every single majority vote. It's just a mathematical impossibility. The majority element is absolutely guaranteed to have at least one vote left standing at the end, which means it will be our final candidate.
And that is the true power of this approach. We get that perfect O of n time because we only look at each element one time. We get that beautiful O of 1 space because all we ever need are our candidate and our count. And it doesn't care about negative numbers or duplicates, it just works. Plus, since we were guaranteed a majority exists, we don't even need a second pass to verify the result. It's a one-and-done deal. It really is just a fantastic example of clever, elegant problem solving. Instead of taking the brute force path of counting everything, it finds this simpler underlying truth that opposing forces can just cancel each other out. And it builds an incredibly efficient solution around that single idea. And that brings us to a final, really important thought. This algorithm is so great because we were promised a majority exists. But what if that guarantee wasn't there? What if a majority might not exist? The algorithm would still give you a candidate at the end, but it might not be the real winner. So how would you change it? How would you adapt this to verify the result? That's your next challenge. Thanks for joining me on this explainer.